All right, welcome back, everyone. I hope the exam went well for you this past week. It's just a reminder, or this past Monday, not last week. Just a reminder that the final exam is not going to be cumulative. The final exam is only going to include the material that we have done recently. So it's only going to include lectures 27 through, what do we go up to, 34, I think. Yeah, so it's only going to include that material, though it will be worth a bit more. I think it's going to be worth 20% of your grade, if I'm not mistaken. So it will be worth a bit more than the other ones, but it'll effectively be midterm 4. So that's how that's going to work. Anyways, let's keep going with our current discussion here. So as I said last time, what we're going to do in this last part of the course is we're going to try to develop higher dimensional versions of the fundamental theorem of calculus. And basically the fundamental theorem of calculus says that derivatives and integrals are in a certain sense opposing operations or inverse operations of each other. And you could use certain theorems in order to get them to cancel out in a particular way. So an integral and derivative will kind of disappear in a very particular way if you combine them together. That's what the fundamental theorem of calculus says. All right, so last time we talked about vector fields, which is where we assign a vector to every single point in space. And that's going to become relevant today. And in the future, it's going to be relevant to our new versions of the fundamental theorem of calculus. But before we do any of that, we need to review some parametric equations. I know we went over this stuff in calculus 2, but that's definitely been a while at this point. So let's go ahead and review some of this stuff. So the first thing here is if you want to have a line segment from x0, y0 to x1, y1, where specifically you'll be at this point at t equals 0, and you'll be at this point at t equals 1. It's going to follow these parametric equations right here. 1 minus tx naught plus tx1, and then y is 1 minus ty naught plus t times y1. And you can see why this would be true. If I plug in t equals 0 here, we're going to get 0 for these. So these will go away, and we'll have 1 minus 0 will be 1 for these. So at t equals 0, we'll have x is x naught and y is y naught. And then the reverse thing will happen when we go to t is 1. When t is 1, these will both be 0, and then these will both be 1. So we'll have x is x1 and y is y1. So if you want to draw a line segment between these, this would be how you do it. All right, next we have the circle of radius r centered at the origin, although it's not too hard to generalize this to being centered elsewhere. So if we have a counterclockwise circle, meaning we traverse the circle in this direction, we have x is r cosine of t and y is r sine of t. That will do the trick there. But if you want to go around a circle in the clockwise direction, we have x is r cosine of t and y is negative r sine of t. Now, where do these come from? This comes from switching t with negative t. So another way of writing this is like this. So when we increase t, we'll go in the opposite order here. But remember, cosine is what's called an even function. So it eats its negative signs and gets rid of them. And sine is an odd function. It spits out its negative signs. So that's how we get the form that's written right here. All right. And then if you want to center it somewhere other than the origin, like maybe you want to center it at the point HK, then what you would do is you would simply just add the coordinates for your center to the end of these equations right here. That's all you have to do to change them for parametric equations. All right, finally, similar to a circle, we have an ellipse. So with an ellipse, rather than having the same coefficient for cosine and sine, we're going to have different coefficients depending on how these are weighted. So for example, if we have x squared over a squared here, our x is going to be a cosine of t and y will be b sine of t. So if we have something that looks like this and we want to traverse it counterclockwise, this would be the way to go. And in a similar way, if we want to traverse the ellipse the other way, we would use this, kind of similar to how we put a negative sign right there. All right. Now remember the interpretation of parametric equations. I want you to remember the physics interpretation of this because I think it's a useful way of thinking about it. Remember the parametric equations can represent a particle's position at a particular time. So oftentimes there are multiple ways to trace out the same shape with parametric equations, but the path each particle takes will be different for each representation. So even though we trace out the same path going this way around the circle, and we trace the same path going around this way, where the particle is at different times will be different between these. And for some applications, actually for a lot of stuff we're going to be doing today, that difference is noticeable. So we want to be able to recognize different ways of representing the same curve. All right. That's kind of a basic review of parametric equations, and we'll be using lines, circles, and ellipses a lot. All right, so far we've studied some various types of integrals. Well, we know the traditional Calc 1 integral from a to b of f of x dx. We have the double integral over a region, which measures the volume under a surface. And then we have the triple integral, whose physical interpretation is a bit harder to understand, but is analogous to each of these, and its domain is three-dimensional. So now we'll introduce a new type of integral called a line integral. So if the three that we had weren't enough, we're going to have another one here. So we're going to have a line integral, and this is written a bit different. So this is almost kind of written the same way that double and triple integrals are, where they have just a letter representing the region here. Only it's not going to be in terms of these two bounds right here. It's just going to be over some general curve C right here. Uh-oh. Why does this always happen like after? All right, hopefully that's better. Okay, so what does this new integral mean? And notice a difference here. So the previous, our traditional Calc 1 integral is dx, but this is ds. And rather than just being between two different x values right here, this curve could traverse and be any which way through space. So I'll explain a little bit more what I mean about that in a second. But let's talk about the formal definition here. The definition of a line integral of f along C is the sum from I equals 1 to infinity. So this is going to be a type of Riemann sum. We have f of xi, y sub I, and then we have delta s right here, where delta s is a tiny distance along the curve C. And this is a point taken somewhere from within that tiny little section of distance here. So this is effectively our Riemann sum version of this right here. But what is it going to be in practice? So naturally with integrals, we don't want to have to do a Riemann sum every time. That's going to be rather tedious. How are we going to do this in practice? Well, if we can parameterize our curve, so we have a curve C that we have parametric equations for, and they go through, say, x and y, and then our t ranges from a to b, then what we can do is we can rewrite this where we plug in our parametric equations. Now, what we could do is we can change ds into t's, because now we have our variable in terms of t, right? So let's remember what ds is right here. ds is the square root of x prime squared plus y prime squared dt. Because if we were to look at this another way, we have ds dt, which you may remember this was called the speed, that had this definition where we have x prime squared plus y prime squared. So that means that ds as a differential is going to be the square root of x prime squared plus y prime squared. Another way of writing this is it's the magnitude of our velocity right here. So this is another way of imagining this. Yeah, what dimension is the essence of what's going on here? I'll show you that on the next page. I'll show you a visual representation of what's happening with this. So anyways, we can change this integral into the integral from a to b. So now it's an integral with t's. We have x of t and y of t plugged in, and then we put this. We have the magnitude of r prime of t dt. So in practice, most of the time when we do a line integral, this will be the way that we imagine it. We're not going to do any Riemann sums. I'll just tell you that right now. We're not going to do any Riemann sums with line integrals. We're going to be looking at them in this form right here. Okay, but what does this mean? This just kind of seems like we complicated the Calc 1 integral and made it worse. And in a certain sense, that's almost right. The line integral is a type of generalization of the integral from calculus 1. So let me show you a picture that will hopefully bring this to light here. All right, so if f of xy is greater than or equal to 0, then the line integral is the area under the surface and above the curve C. So back when we were in Calc 1, our interpretation of the integral was the area under a curve, provided that our function was positive. And I want you to think of the Calc 1 integral as a flattened curtain. So we kind of have this curtain and its length varies depending on the function, but it's kind of flattened into the xy plane here. The line integral does the same thing. It's effectively a curtain that has a variable height, only this time we could have a twisted or non-flat curtain. We're still doing an area under something, but this time our domain, rather than being a perfectly straight line, can be a curve that goes through two-dimensional, or as we'll see, three-dimensional space as well. So effectively, we're measuring the area under the surface that's above this curve right here. So if you were to flatten this out, you would just return to a Calc 1 integral here. So you can almost imagine that the Calc 1 integral is a special case of this right here. Why is it twisted? Because if it's not twisted, then our curve would have just been perfectly straight, like this, and we would have had a Calc 1 integral or something like that. But since our curve is not confined to the coordinate axes, our curve or our domain can kind of twist around, like it can move through 2D space, and it kind of makes this sort of curtain that like is not confined to the plane right here. Is the domain within the solid? The domain is in the XY plane. So this curve can meander anywhere it wants in the XY plane right here. And then our area will go right above that curve right here. All right. Can I show the bottom of the last page? Yeah, here it is. Okay. Now, one thing I want to say about this before we move on. So we found, actually, it's good that we came back to this. We want to, when we do these integrals in practice, we usually come up with a parametric equation that represents our curve, that like kind of moves along our curve, whether it be a line or circle or parabola or whatever. But you might ask, okay, well, remember there are multiple parameterizations for the same shape, right? Like we saw two different ways to make circles, two different ways to make ellipses on the previous page. Would my integral change if I decided to use a different parameterization of whatever shape it is? And the answer is no. So for example, if my curve were like a circle, like I had a circle and then I had my function kind of going above like this, and I had my curtain looking like that, it doesn't matter whether I spin around the circle this way or if I spin around the circle this way, because it represents this area right here. It's going to be the same no matter what. So this does not depend on which parameterization we try to use. And that's good news. That means we could just pick the first one we think of or the easiest one, and we could just use that. All right. Now, one thing we need to watch out for is, especially for things like circles, we need to make sure we're not going around the shape multiple times. That would mess things up. So if you have a circle, make sure you're only going from 0 to 2 pi, or however long it takes to get around. Is there a case where it will matter? It's not going to matter in the evaluation of these integrals, but the type of path we use will matter later. Yeah, like so different paths will end up mattering later, but not for evaluating these integrals. All right, and finally, what you could do is if your C isn't just one curve, like maybe we have this shape right here, and then we have it going straight for a little bit, then maybe we have it go around like this, and then it goes this way. What you could do is you could just do the line integral of each of these separately and then just add the results together. So this is kind of like back in Calc 1 where we had the integral from a to b, and then we added the integral from b to c. That was the same as the integral from a to c. So this is effectively the line integral version of this. So if we could break up c into a finite number of these curves here, then this is going to be the integral over c1 of this, and then we go over c2, and we keep doing this, and then until we finally get to the last segment of the curve, cn. So we simply add all of those together right here. Are we finding the area of the curtain? Yes, that's exactly what's happening. So this line integral right here, if we kind of drop down these lines right here, we're finding the area of this curtain or this shape right here. And unlike in Calc 1 where the curtain was kind of stretched out along the plane, this one doesn't need to be that way. Our curve can be kind of anywhere we want here, not just on an axis. All right, so let's actually go ahead and do this. Let's try to compute one here. Maybe that'll make things a little bit more clear. All right, so what we're going to do is we're going to evaluate the line integral xy ds, where c is the part of the ellipse x squared over 4 plus y squared over 16 in the first quadrant, and it's oriented counterclockwise. All right, so what does that mean? Well, if this is the xy plane here, not the x plane, the xy plane, we're starting here at this point, and we're moving along the curve this way here until we end up at this point. Now, as I just said, we could have also found a different way of parametrizing this, but it still would have ended up being the same right here. All right. Oh, does Cn approach to infinity or some number? Oh yeah, it only works for a finite number of these. Yes, so n has to be a finite number, like 10 or something. You can't break it up into infinitely many pieces. That's going to cause some issues. All right, so before we do this, we need to come up with a parameterization of our ellipse. And thankfully, we just reviewed that. So if I want a counterclockwise parameterization of my ellipse, what is x going to be? What am I going to write for my x parameterization based on what we learned earlier? 2 cosine of t, that's right. So for x, we traditionally use cosine, and we use the square root of this number right here. So following that reasoning, we're going to use sine for y, and we're going to have the square root of this number, which will be 4. And you could see that these parameterizations will work out if you substitute these in here, because you'll just end up with the Pythagorean identity. Sine squared plus cosine squared is 1. That's how we know that those are going to be right. All right, so let's see here. Now that we know our parameterization, let's go ahead and do this line integral. So we begin like this, but usually we don't do line integrals in this form. What we're going to do is we're going to turn everything into t's. So we have x, that's 2 cosine of t, and we have y, that's 4 sine of t. Now we're missing something here. We're missing what this ds is, right? So what's going on with that? Well, ds is the magnitude of r prime dt, or it's the square root of x prime squared plus y prime squared dt. Okay, so I guess we need to do some derivatives and plug them in here to see what this is going to be. So x prime is -2 sine of t, and y prime is 4 cosine of t. All right, so then if we put a square root here and we square these, we have 4 sine squared of t plus 16 cosine squared of t. All right, and then now we replace our c, just kind of a generic curve here, with specific t values. So this point right here, this begins at t equals 0. T is kind of like our angle in this case. And it seems like we go all the way to t is pi over 2. So effectively what we've done is we converted this line integral into an ordinary Calc 1 integral. You can almost imagine that we're kind of stretching out the curtain and then just using Calc 1. to find the area under it now. All right, so let's see here. Now we actually need to do this integral. Let's get all of our coefficients pulled out of here. So I can factor a 4 out of here, and when it moves out of the square root, it becomes a 2. 2 times 4 times 2 is 16. So I have 16 cosine of t, sine of t, and then I have the square root of sine squared plus 4 cosine squared. Okay, now this almost looks like it could be a Pythagorean identity, except that their coefficients don't match. We have a sine squared here and a 4 cosine squared right here. So what I'm going to do is I'm going to change this into cosine squared plus 3 cosine squared. And then I'm going to combine these two to form 1. So my integral ends up turning into this right here. All right. Why did the 4 and 4 cosine not get squared? Oh, it did get squared. Yeah, so we'd have y squared, so we ended up with 16 cosine squared right here. All right. So how are we going to do this integral now? Let's see. I see some stuff under a square root, and I see some other stuff out here that kind of looks like the derivative of this. So I'm going to use u sub. All right, so I'm going to have u is 1 plus 3 cosine squared of t. And du, well, let's see. So I use the power rule. Well, the derivative of 1 is 0. And then I use the power rule. I have 6 cosine of t, and then the derivative of cosine will be negative sine of t dt. All right. And then finally, I guess I don't have a 6 here, so I'm just going to divide by negative 6. We have cosine of t, sine of t dt. And that we do have in our integral, so that's good. All right, now we have negative 16 over 6. And then if we convert our bounds here, which I always like to do, I put 0 in here, and I have 1 plus 3 is 4. And then I put pi over 2 into here. Cosine of pi over 2 is 0, plus 1 will be 1. And then we're going to have the square root of u du. Okay, now this is a bit backwards, but we gained a negative sign, so why don't we use our newly gained negative sign to flip the order of this integral into the proper order here. All right, what if we didn't convert? Then you could just plug the numbers back in later. All right, and then we could just go ahead and use the power rule on the square root of u. So this is u to the 1/2. We raise that, it becomes u to the 3/2. And then we divide by 3/2 or multiply by 2/3. And this goes from 1 to 4 right here. What happened to the negative? We used the negative to flip the integral into the proper order right there. All right, and then finally we'll plug in 4 and 1 here. Actually, let's see, this is 16 over 9. 4 to the 3/2 is 8. 1 to the 3/2 is 1. All right, so the a minus 1 is 7, I think. And then we do 7 times 16 and get 112. So we end up getting 112 over 9 for this one right here. Can I explain how I got 1 plus 3 cosine squared? Yeah, so after I simplified it here, I had sine squared plus 4 cosine squared. So I split this up to be cosine squared plus 3 cosine squared, and then I combined the sine squared and cosine squared to get 1 right here. And then I have the 3 cosine squared left over. All right, this is actually kind of the reverse of the problem we usually have. Usually the integral is really hard to set up, but doing it's easy. This was actually a harder integral than average. But setting it up wasn't too bad. But hopefully you understood, hopefully you focused on this part up here. This was the main point up here. What are these used for? We'll see an application later in class. All right. So in the previous problem, we had our curve go through 2 dimensions. So our curve or our domain that we're integrating over can go through X and Y, and then the height of our curtain is measured by Z. But there's no reason why we can't have our curve go through X, Y, and Z, and then have our height of our curtain measured by a 4th variable, like maybe W or U. Now, kind of like how we lost the geometric interpretation when we moved to triple integrals, we're losing that nice, easy to understand curtain interpretation when we move to paths that go through 3-dimensional space, because this is technically the best way to draw this would be a curtain in 4D space, and that's not hard. That is hard to draw. So we kind of lose the geometric interpretation here, but thankfully doing the integral is going to be pretty much the same as it was before. So we have f of x, y, z ds. We could substitute in x, y, and z, our parametric equations for these, and then our ds will turn into the magnitude of r prime dt right here. So doing them is pretty much the same as doing it when our path was confined to 2 dimensions. So let's go ahead and give it a shot. Let's see if it really is that easy. Evaluate the line integral of x plus y plus z ds, where c is the helix, r of t is cosine t, sine of t, and t, and we're following along the helix from 0 to pi right here. All right, well, let's see. So we have our parametric equations. They were kind enough to provide those for us. So let's go ahead and rewrite our line integral in parametric form, or with respect to dt. So they actually gave us our a and b as well. So they're pretty nice on this one. We know this is going to go from 0 to pi. X is cosine of t, y is sine of t, and z is t. All right, now we can't forget to include the magnitude of r prime here. So let's figure out what that is. So r prime, let's see. So the derivative of cosine is negative sine. The derivative of sine will be cosine. And the derivative of t will just be 1. All right. And then when we do the magnitude of this vector, this is the square root of sine squared plus cosine squared plus 1 squared, or 1. And this ends up simplifying to something pretty nice, because we know that sine squared plus cosine squared will always be 1. So this is square root of 1 plus 1, aka root 2. So our r prime is pretty simple this time. It's going to be root 2 right here. And then we have dt. All right, and then now we just need to integrate this. So whenever we convert the line integral into a parametric integral, you can almost imagine, I think I said this before, you're kind of stretching out the curtain along one axis. You're just finding the area under it that way. So this takes a Calc 3 problem and turns it into a Calc 1 or maybe 2 problem, depending on how hard it is to integrate. All right, so we go ahead and integrate cosine. Well, let's keep the root 2 out here. We go ahead and integrate cosine, we get sine. We integrate this and we get negative cosine. And we integrate this and have t squared over 2. All right, and then now we can plug in the numbers here. So we plug in pi. We have sine of pi, which is 0. We have negative cosine of pi, which is positive 1. And then we have pi squared over 2. And then we plug in 0. Sine of 0 is 0. We subtract negative cosine of 0, so that's adding 1 again. And then we put 0 in here. All right, so all in all, this ends up being root 2 times 2 plus pi squared over 2. So lots of 2's involved with this line. All right, but hopefully this demonstrated that while it's hard to imagine what this represents, kind of like how we could imagine maybe the previous ones, it's easy to compute. It's not any harder to compute than the ones where the path only went over x and y here. Now, just like, I want to say one more thing, just like triple integrals, it might kind of seem like, oh, well, because it has this really weird geometric interpretation, they're not going to be useful. It does turn out that even line integrals like this will end up having uses, and we'll actually see those at the end of class here. Okay, now it turns out that these are called scalar line integrals, where we have a scalar function of x, y, and z right here, and then we go over a path c. We go over the tiny chunks of the path right here. Oh, why do we multiply by the magnitude? Remember that ds is the magnitude of r prime times dt. So this is just another way of writing ds. That's where we get that from. What do I mean by stretching out the curtain? Let me go back to my picture here. So let's say we have this, right? And it's kind of twisted. So like you kind of have it puffed out in the x direction here. What I mean by stretching it is we take this and we kind of pull it both ways here. So we can almost kind of imagine that we're taking this curtain and we're stretching it along, I guess in this case, the y-axis. And when we do that, it turns into an integral that looks like this, because this domain is just along an axis, and then we look at the area under there. All right, so that's what's going on here. I need to move on to the next part here. So kind of like how we could have a scalar line integrals, it turns out there's also something called a vector line integral. So suppose that f is one of those continuous vector fields that we introduced last time. So remember, a vector field is a way of assigning each point in space with a particular vector. Let f be a continuous vector field defined on a smooth curve C. The line integral of f on C is given by this right here. So we have f, so this is like the function, and then we have t hat, which let's remind ourselves what t hat is right here. Actually, do you guys remember what's t hat? Yeah, it's the unit tangent vector. Do you guys remember the formula for it? R prime over the magnitude? That sounds right, Michael. So it's going to be r prime of t divided by the magnitude of r prime of t. So this is our unit tangent vector. And why is this in here? Why did we just randomly throw this in here? This represents the direction of the curve. Because remember, let's say our curve looks something like this, right? If we were looking at which direction the curve is going at this point, then t hat would give us the best idea as to which way this is going. And we want it to be a unit vector so it doesn't affect the size of this integral. We just want to specify a particular direction right here. All right. So now, I guess we could do this integral like this, but having ds is kind of awkward. So kind of like with the scalar line integrals, we're going to find a better way of doing these than before. So let me make sure I go in the right direction of this. Let's see. So we just reminded ourselves what t hat was. T hat is r prime of t over the magnitude of r prime of t. Now we also have a way of representing s to kind of look like this. ds is the magnitude of r prime times dt. And then we have a nice cancellation happening here. So probably a better way of thinking about these vector line integrals would be to dot f with r prime of t and then just have dt at the end. And it's at this form right here. This is the way that we're actually going to end up computing these the majority of the time. Kind of like how we switched into parametric for the other ones. This will be the way that we're actually going to end up doing these right here. All right. So let's see here. Another way we can think about this is if we write f as its three components, p, q, and r. And remember, each of these are functions of three different variables. So we have p, q, and r here. For each of the component functions of r of t, we can write this. dx is x prime times dt, dy is y prime times dt, and then dz is z prime times dt. And where do these come from? If we divide both sides by dt, we have x prime as dx dt, and so on. All right, so what's another way of expressing this vector line integral, well, it's a dot product of f with all of these derivatives, right? So we could write this as p times dx, because this right here would give us x prime dt. And then we have q times dy, and then r times dz. So this is another way of doing this integral. And what we would do in practice for this version is we could break this up into 3 separate integrals and do 3 different Calc 1 integrals right here. All right. R prime represents what again? It's the derivative. So if R is our parameterization for our curve, R prime represents velocity or the rate of change of that curve. But this is another way you may see these vector integrals represented in the future. I personally kind of prefer this way of doing them, but this right here is something you also might see. Okay, here's kind of a summary of everything that's happened so far with these, and then we'll actually do one. The line integral of a vector field over an oriented curve C parameterized by R of t is this, can be expressed in this way. So this is kind of just redoing everything we just did here. So we did this part in the first section of the last page. We wrote this right here. And then one way of writing this now is P, Q, and R is F, right? So if you look closely, this is actually a dot product with what's called dr, where dr is dx, dy, and dz. So you can almost think of this as like a differential vector right here. So a final way of looking at these line integrals with vector fields is f dot dr. And this is a very common form if you do physics. This is probably how you'll see line integrals a lot in that case. Now, what do line integrals represent? So these scalar line integrals represent the area under this curtain that we drew. What do the vector line integrals represent? This line integral is a measure of how much the vector field points in the direction of C. Okay, so what does that mean? So let's think about the dot product, right? So if 2 vectors are parallel to one another, the size of the dot product is larger. But on the other hand, if 2 vectors are close to being perpendicular, meaning they're going in opposing ways right here, then the size of the dot product is smaller. Okay, so what is this saying? Well, remember, t represents the direction of our curve, right? This is the direction of our curve here. Now, if f is going in the same direction as our curve, we're going to be accumulating a lot of value for that, because going in the same direction means that you're parallel, so you're going to be having big dot products for that region. On the other hand, if f is going perpendicular to the direction of your curve, then these dot products will be very small. So this is just like I just said right here, this is a measure of how much the vector field kind of agrees with the direction of the curve right here. That means smaller or closer to 0? Both. Yeah, the magnitude of this, the magnitude of the dot product will be close to 0. All right. Well, enough talking about what this is. Why don't we actually go ahead and compute it here? So calculate the vector line integral here, given that our vector field is yz, xz, and xy, and C is parameterized by this curve t, t squared, and t cubed, from t going from 0 to 2 here. All right, well, let's see here. Probably the most common form of our line integral that we're going to see for vector line integrals will be this: f dot magnitude of r prime, or sorry, just r prime, dt right here. And this will go from 0 to 2, like that. What was the physics application I circled up there? If this is going to show up in a physics application that I'm going to talk about in a minute here. All right. So let's see. Let's do this dot product. Now, before we do this dot product, we need to know two things. We need to know what f is in terms of the parametric equations, and we need to know what r prime is. So let's kind of compute that on the side here. So if we convert f using the parameterization of our curve right here, then what are we going to get? We're going to get, let's see, y times z will be t to the 5th. X times z will be these two. This will be t to the 4th. And then we have xy, which will end up being t cubed right here. All right. And then what's r prime? Well, let's see. The derivative of this will be 1, and then we have 2t, and then we have 3t squared. Okay, now let's proceed to take the dot product of these and then do the integral. So we have t to the 5th times 1, so that's t to the 5th. And then we add t to the 4th times 2t, so that's actually adding 2t to the 5th. And then finally, we do t cubed times 3t squared right here. So that's 3t to the 5th right here. How did I get f? Well, I took that this was x, this is y, and this is z, and I substituted it over here. Okay, now all of these are t to the 5th, so there's no reason why I can't combine all of these together. So this is 0 to 2, t to the, nope, not that, t to the 5th. Oh, the 6 comes up here, that's what I was thinking, dt. All right, then when I integrate this, then I'll get the 6th power. I was a little bit ahead of myself here. I raise this to be the 6th power, I divide by 6, so I just get t to the 6th. And then we do 2 to the 6th power, which if I'm not mistaken, is going to be 64 right here. All right, so this is what we ended up getting for our vector line integral. Now, one interpretation of the vector line integral you can make is that when two vectors are anti-parallel or close to being that way, so like if we have vectors that look like this, then the dot product is negative. So what this is saying is that more often than not in this curve, the force is going in the direction of the curve. If it were going in the opposite direction of the curve, we actually would have ended up with a negative result for this, because our dot products would have mostly been negative for that, and we would have accumulated more negative than positive. So this means that f is going in the direction of C in general. All right. Now, people were asking, okay, what are we going to use this for? This seems kind of weird. What we're going to use this for is computing work. Now, you might be like, okay, well, if we computed that last semester, right? So we spent a lot of time computing work in calculus too. You at least had me or Carol DeMoss for that class. And the answer is that last semester we focused on a force that could change somewhere along our path, but our path was still straight. In this class, we're going to fully generalize it, and now we're going to be able to have paths that kind of weave through space rather than just going in a straight line. Because the basic definition is just force times distance in a straight line, but now we don't even need to do that. Now we don't even need to go in a straight line right here. Okay, so how is this going to turn into a line integral? Well, let's take a look here. Let's consider an object moving along a path C in the field. At each point C, we consider the projection F dot T hat of the force onto the unit tangent vector. So this is effectively measuring how much force is moving us in the direction that we're going. So the more the force agrees with the direction that we're moving in, the more work is being done. So let's see here. We have the force in the direction of t hat, the direction that we're moving. Now, in order to figure that out, that's going to be the scalar projection of F onto t hat, which is the magnitude of F times cosine of the angle between them right here. All right, now what's cosine of theta? Well, remember that F dot t hat is the magnitude of F times the magnitude of t hat cosine of the angle between them. So if we want another way of writing this cosine right here, what we could do is we could just divide by these right here. So this cosine of theta is going to be F dot t hat divided by these two magnitudes. Okay, and that will be cosine of theta. All right. So let's simplify this a bit. We notice that we have a magnitude of F up here and a magnitude of F down here. So those will cancel. Now, what's the magnitude of t hat going to be? What's that? It's just 1, right? Because t hat is a unit vector. So this further simplifies to just be F dot t right here. So that's what the force in the direction of t hat is going to end up being. Now, I think someone was mentioning earlier, force or work is ultimately equal to force times distance. What's the distance that we're traveling over here? Well, the magnitude of our force is this F dot t hat we just found. And the distance that we're going is going to be this delta SI. So what we do is we effectively divide up this curve into a very large number of these straight lines. And we compute the force along each of these straight lines, and then we have more and more of them. And when we have more and more of them, they'll follow the curve more closely until ultimately we're going to end up with an integral. So as we have more of these and as the size of them goes to 0, our work will turn into the line integral of F dot t hat ds. But a more common way of seeing this in physics is you'll see this as F dot dr, like this. This is probably the more common way of seeing it with physics right here. Was this proof to explain, or we need to know this? Yeah, no, this isn't a proof-based class. You don't need to replicate that or anything. All right. So with that being said, let's go ahead and compute our computer work example here. So suppose an object moves from 1, 0 to 2, 1 along the parabola x equals y squared plus 1, subject to the force F equals x squared y e to the x. Find the work done on the object. Okay, so what we're going to do, we have this curve here, right? This is a parabola, x equals y squared plus 1. And we're moving from the point 1, 0 to the point 2, 1. I guess this isn't quite drawn to scale, but so be it. So we're kind of moving over one arc of this parabola right here. All right, now when we do line integrals, we usually want to find a parameterization of our path, right? So what would a parameterization of this path be? Well, this is what I like to call the dumb parameterization. If you have one variable as a function of the other, what you could do is you could just have the variable involved with the function being t, and then the other variable being whatever the function is. So in this case, we would have y of t being t, and then x of t being t squared plus 1, because you could easily substitute the y into that, and you have y squared plus 1. So this is definitely a parameterization for this parabola right here. And it looks like we're going from t is 0 to t is 1. All right, so let's go ahead and do this. We're trying to compute F dot dr here. And the way we're going to imagine this is f dotted with r prime of t dt. Okay, let's see. So our f in terms of t will be t squared plus 1 squared. That's what x squared is. And then we're going to have t e to the t squared plus 1. So this is what f is right here. And then r prime, let's see, the derivative of x will be 2t, and then the derivative of y will just be 1. And this will go from 0 to 1. All right, so we go ahead and do this dot product. And we have t squared plus 1 squared times 2t plus 1 times t e to the t squared plus 1. Why did I make y equal t right here? Yeah, to make an easy parameterization. Whenever you have one function or one variable in terms of the other, you could just make the independent variable be t and the dependent variable be the same formula, only with t's instead. You could do that with any function you want. All right, and then we just have to do this integral right here. So I'm going to FOIL this and multiply by 2t. So t squared times t squared is t to the 4th, and then times this will be 2t to the 5th. T squared times 1, and then 1 times t squared will give me 2t squared, times 2t will give me 4t cubed. And then I do 1 times 1 is 1, times 2t is 2t. All right. And then all we need to do now is do the polynomial integral for these. So we raise this to the 6th power, divide by 6. We have t to the 6/3. We raise this to be the 4th power, divide by 4. And then we raise this to be the 2nd power, divide by 2. And then now we need to do this. So how are we going to do this integral? Well, let's try u sub. So u will be t squared plus 1, and du over 2 will be t dt. So we already finished up this part of the integral. And then we're doing the integral of 1/2 e to the u du right here. All right, and then let's see here. Our new bounds for this will be 1 to 2. So when we finish this up, we plug 1 in for all of these. So we have a third plus 1 plus 1. And then we have plus 1/2. And then we have the integral of e to the u is e to the u. And then we plug in 2. And we subtract, and then we plug in 1. So there's e. So we end up with this sort of convoluted looking answer here, which I guess we could simplify to be, what, 7/3 plus 1/2 e squared minus e. So this is going to be our integral here. Okay, now actually there's another way of doing this integral. So I want to at least briefly talk about the other way of doing it. I'm not going to do the full thing because we already did this. Remember earlier that another way of expressing these vector line integrals is this way right here. So we could do, or actually not, I don't want it that way. I want to talk about it this way. So one way of expressing our vector integrals here is by doing p dx plus q dy plus r dz, or just these two, if we only have 2 dimensions right here. So what if we tried to do the integral that way? So if we had the integral of f dot dr, we could write it as p dx plus q dy over this curve. Okay, now what is p? Well, p is the name for the x coordinate of our vector field, and q will be the y coordinate. So p is x squared, we do that over x, and then q is y e to the x, and we do that with a y here. Okay, now this integral is actually all ready to go because we have all of the variables being the same thing right here. But this one's a little problematic because we don't have a y up here. But the good news is that we actually have a nice relationship between x and y. X is equal to y squared plus 1. So this is the same thing as doing this integral. Or y squared plus 1. I don't know if I said that or not. All right, so now we have a y integral here, an x integral here, and we know that in our problem, x ranges from 1 to 2, and in our problem, y ranges from 0 to 1. So we end up with this right here. This part should look familiar. This is literally the same integral that we had back here with t's right here. So we know how the 1/2 e squared minus e will show up. And then this part right here, if we do this, we're going to have 8/3 minus 1/3, giving us 7/3. So this will actually give us the same answer, 7/3 plus 1/2 e squared minus e. So this is sort of an alternative way of doing these integrals. The trouble is that sometimes it's not quite easy to turn these variables from one into another. So this method can be harder to use sometimes than the parametric way. But this is a nice alternative. And I think in this case, at least, it actually took less work than this one right here. All right. Oh, I'm sorry I went over, guys. Sorry about that. All right. Next time, we'll finally get to something called fundamental theorem of something. So we have that to look forward to next class. So I'll see you guys then.
Excuse me, Professor.
Yeah.